Today we want to continue doing some problems. In chapter 6, section 3, question 3, we just had, had to pick which graph we're going to choose, and they gave us a choice of 5 lines. So the thing that makes us want to draw a line is the fact that we're drawing a graph of velocity, and we're told that we should assume constant deceleration. So we should assume that derivative is constant, and that means we want to draw a linear function. So we'll just start off at 90 feet per second. That's going to be our speed in foots per second over time, which is measured in seconds. So there we are, going from 90 feet per second down to 0 feet per second in 6 seconds. What's interesting about this problem is that we're given the velocity, and the velocity is the derivative of position, and the derivative of velocity is acceleration. So velocity is sitting in the middle. We can differentiate to get down to the acceleration. We could integrate to get up to the position. So the two questions that I've added to this problem: how far does the car travel in 6 seconds, and what is the acceleration of the car? One is an integral question, and the other one is a derivative question. Since we're looking at a graph, the integral question should be an area under the curve, and the derivative question should be a slope of the tangent line. So this encompasses the two questions that we have, the two big questions of calculus that we talked about at the very beginning. What's the slope of the tangent line? And what's the area under the curve? So that's why and those are both going to be easy to calculate because we have constant deceleration. So the slope of the tangent line is the change in velocity, negative 90 feet per second, divided by the change in time, 6 seconds. So negative 15 feet per second squared. The other question says, how far did the car travel in 6 seconds? And so that's, since that's a question about position, which is the integral of velocity, and integrals, when we're looking at a graph, is going to be an area under the curve. So the area is just the area of a triangle, 1/2 the base times the height So the car travels 270 feet in the 6 seconds, and its acceleration is negative 15 feet per square second. Any questions? So we can ask variations of this question. Normally, when we're looking at data from a car, we don't know that the car takes 6 seconds to come to a stop. Usually this is listed in as a distance, the stopping distance. So we could say an alternate version of this problem: a car going 90 feet per second comes to a stop in 120 feet. So we have all these different we have a different setup of information. In this case, so the given information was the initial velocity, how long that took in seconds, And then we had questions about distance and questions about slope of the tangent line. So in this alternate version, I've just given two different pieces of information. I've said the car going to 90 feet per second comes to a stop in 120 feet. And so I could ask, how long does this take? I could ask a question, how long does it take a car to stop? And I could also ask, what's the acceleration of the car? So in this case, we're going to draw a similar picture, assuming constant acceleration. So we're going to draw the same picture, or a similar picture, where we start off at 90 feet per second. But now we don't know how long this is going to take. So this stops not at 6 seconds, presumably less than 6 seconds, because it does so in 120 feet. So we don't know what that is. I'm going to call that t naught when it's going 0. So there's t in seconds. And here's our velocity in foots per second. So in this case, the information that we're given that the car went 120 feet. So we're told that the area of this triangle scooch that up. The area of the triangle, which is 1/2 times t naught times the height of 90, is equal to 120. So we're still doing the same thing. And then we don't know the acceleration, but the slope is a decrease of 90 feet per second in t naught seconds. So to figure out the acceleration, we'll need to know how long it took to come to a stop in seconds, not in feet. And to get there, we'll have to use the area. Since we know that we're assuming constant deceleration and it took 120 feet to come to a stop, we can solve the area equation for t naught. So it's going to be 240 over 90. Or let's see, take out a 3, so 8 divided by 3 seconds. That's a weird way to write it. Let's call it 2.67. Now that we know it took 2.67 seconds to come to a stop, I can calculate the acceleration by taking 90 and dividing it by the 2.67. Dividing it by the 8/3 seconds and get the acceleration in feet per second. So it's going to be 270 divided by 8. It's going to be 270 divided by 8. So 135 divided by 4. Any questions? So arithmetic is hard today. So 50, 15, 2.5, 50, 15, 2.5. So 65, 67.5 divided by 2. So cut that in half. It's going to be 33.5 and 0.25. So is that going to be 33.75? Any questions? I have a calculator right here. I don't know why I'm Turns out I was right. That's kind of amazing. I did arithmetic successfully. The day before a holiday. That's amazing. Any questions?
Why would you divide by 8/3 instead of just 2.67 seconds?
So I wouldn't have to reach for my calculator.
Oh, okay.
Because then I knew I just do 270 divided by 8. Then I hit an odd number when I did. And that just means I'm going to divide by 2 3 times. Then I hit that odd number. But then I just started breaking it up. 100 divided by 2, 30 divided by 2, 5 divided by 2. So specifically because it was an 8. If it was something else like a 7, then I would have just grabbed the calculator right away. But dividing by 8 is dividing by 2 3 times, and dividing by 2 is pretty straightforward. Any questions? Comments?
For this problem, would we also find the position?
The position is wrapped up in the 120 feet. So we were told that the car went 120 feet. In the previous problem, we were asked to find how far the car went, so we had to find the 270 feet. But in this problem, it was given to us. Any other questions? Right. Let's pause the video here and look at the next problem.